Alright, let's go. Number 7. The equation that demanded a mirror universe. In 1928, at Cambridge, a young theoretical physicist named Paul Dirac was trying to solve a problem that had nothing to do with mirror universes. He wanted a version of quantum mechanics that agreed with Einstein's special relativity, one equation that could describe an electron moving near the speed of light. What he wrote down solved that problem. It also broke something else entirely. Physics at the time expected a single well-behaved solution, one equation, one particle, one set of positive energies describing the electron as it was known. Nothing in the framework anticipated a second answer hiding inside the math. But Dirac's equation didn't give one answer, it gave two. Alongside the ordinary positive energy electron, the mathematics insisted on a second solution with negative energy, a particle identical in mass but opposite in charge. Dirac tried to explain it away, proposing a sea of unobservable negative energy states. Most physicists assumed it was a mathematical artifact, an error to be patched rather than a prediction to be tested. Then, in 1932, Carl Anderson at Caltech was photographing cosmic ray tracks in a cloud chamber and found a particle curving the wrong way in a magnetic field same mass as an electron, opposite charge. He had not gone looking for Dirac's ghost. He had found it anyway. Anderson won the Nobel Prize in 1936. The particle was named the positron. Physicists still debate how close Dirac came to fully believing his own equation before the evidence forced the issue. What is not debated is the outcome. Antimatter was not discovered and then explained by theory. It was demanded by theory, reluctantly accepted, and only afterward found in nature. Every particle of ordinary matter, the equation said, has a shadow twin. Number 6. The antimatter that falls the wrong way almost. At CERN, in the antimatter factory beneath the Franco-Swiss border, an experiment called ALPHA has spent over a decade doing something absurdly difficult, trapping antihydrogen atoms, a positron, orbiting an antiproton long enough to study them. Led by physicist Jeffrey Hangst of Aarhus University, the ALPHA collaboration first held antihydrogen in a magnetic bottle in 2010. By 2023, a dedicated apparatus called AlphaG was ready to ask a question general relativity had never actually tested directly. Does antimatter fall down, or does it fall up? General relativity assumes gravity treats all mass identically, matter or antimatter, no exceptions. It's baked so deeply into the theory that for decades, no one thought it needed direct experimental confirmation. Antimatter is so difficult to trap and so violently self-destructive on contact with ordinary matter that the test simply hadn't been done. When AlphaG finally released trapped antihydrogen atoms and watched which direction they drifted, the result, published in Nature in September 2023, showed antimatter falling downward consistent with ordinary gravity, not repelled by it. For a moment, an entire subgenre of physics speculation, the idea that antimatter might be gravitationally repulsive and could explain cosmic acceleration, lost its cleanest experimental loophole. But the measurement was still coarse, with significant uncertainty in the precise gravitational constant for antimatter. Finer measurements are underway. The rule held. Barely. And barely is exactly the word that keeps physicists testing it again. Antimatter obeys gravity. For now, that is settled. But it took 95 years after Dirac's equation for anyone to actually check. Number 5. The excess that shouldn't be falling from the sky. In 2006, the Italian-led Pamela satellite launched into orbit carrying a magnetic spectrometer built to count cosmic ray particles, and, specifically, to measure the ratio of positrons to electrons striking Earth from space. Standard models of cosmic ray physics, built on decades of collision data, predicted that positrons, the antimatter counterpart to electrons, should become rarer and rarer as their energy increases, produced only as secondary debris when cosmic rays collide with interstellar gas. The established rule was straightforward: positron abundance should fall steadily with energy, following a well-modeled curve derived from known collision physics, because there was no expected primary source of high-energy positrons nearby. Pamela's data, published in Nature in 2009 under Piergiorgio Picozza and the Pamela collaboration, showed the opposite. Above roughly 10 gigaelectronvolts, the positron fraction began rising instead of falling, and kept rising. In 2011, the Alpha Magnetic Spectrometer, AMS-02, led by Nobel laureate Samuel Ting of MIT, was installed on the International Space Station and confirmed the excess with far greater precision, tracking it out past 300 gigaelectron volts. Two competing explanations remain on the table: nearby pulsars accelerating positrons, or the annihilation of dark matter particles. Neither has been confirmed. Both remain statistically viable. AMS-02 continues collecting data today, and the shape of the excess at the highest energies may eventually distinguish between an astrophysical source and something far stranger. As of now, no consensus has emerged. Every second, antimatter that should not be there is raining down through the top of Earth's atmosphere, and no one can yet say for certain where it was made. Number 4. The galaxy's core is making antimatter, and no one knows why. In the early 2000s, the European Space Agency's Integral Gamma Ray Observatory turned its detectors toward the center of the Milky Way and found a very specific signature, a bright emission line at 511 kiloelectron volts, the exact energy released when an electron and a positron annihilate each other. That energy signature is unambiguous. It cannot be produced any other way. Astrophysical models predicted some positron annihilation near the galactic center, generated by known sources like supernovae, neutron star mergers, and radioactive decay in stellar remnants. The expected distribution was one that roughly traced the galaxy's star-forming regions, brightest where massive stars live and die. Instead, the 511 keV glow observed by Integral detailed in a 2008 Nature paper, led by Georg Weidenspointner and collaborators, with continued mapping by researchers including Thomas Siegert at the University of Würzburg, is strongly concentrated toward the galactic bulge and asymmetrically distributed in a way that doesn't cleanly match any single known source population. Known supernova rates and stellar populations can account for only a fraction of the observed positron production. Proposed explanations include exotic binary star systems, low-mass dark matter particles annihilating or decaying, and undetected populations of compact stellar remnants, but each proposal, when checked against the total energy output required, falls short or introduces new problems. The debate remains active and unresolved, with dark matter and unseen astrophysical sources still competing explanations more than 15 years after the mapping began. The heart of our galaxy is quietly annihilating matter and antimatter in quantities we cannot fully account for, and it has likely been doing so for a very long time. Number 3. The twin that refuses to be different. At CERN, an experiment named Base Baryon-Antibaryon Symmetry Experiment was built for one purpose: to compare the antiproton to the proton with the highest precision physics has ever achieved. Led by physicist Stefan Ulmer, the Base collaboration trapped individual antiprotons in a Penning trap and measured their magnetic moment, the property that governs how a charged particle responds to a magnetic field. The rule the experiment was built to test comes from C-Pete symmetry, a cornerstone of quantum field theory, which holds that swapping a particle for its antiparticle, reflecting it in a mirror, and reversing time should leave the laws of physics completely unchanged. If C-Pete symmetry is exact, the proton and antiproton must be identical in mass and magnetic moment, differing only in the sign of their charge, no exceptions permitted. In 2017, Base published its results in Nature. The antiproton's magnetic moment matched the protons to within roughly 1 part in 100 million, the most precise antimatter comparison ever made. C-Pete symmetry passed the test. But this created a deeper problem rather than resolving one. If matter and antimatter are this perfectly symmetric, physics has no built-in reason for the universe to prefer one over the other, and yet the observable universe is made almost entirely of matter, with antimatter surviving only in trace, artificially produced amounts. Researchers on multiple teams, including groups searching for even smaller CPT-violating effects at CERN's antimatter factory, continue refining these measurements, hunting for any asymmetry too small for earlier experiments to catch. So far, symmetry keeps winning. The particles are nearly perfect mirror images of each other. The universe built from them is not. Something broke the mirror, and the mirror itself refuses to say what. Number 2. The asymmetry that should not be enough. In 1964, at Brookhaven National Laboratory, physicists James Cronin and Val Fitch observed something forbidden: neutral kaons decaying in a way that violated a symmetry called CP, the combined operation of swapping a particle for its antiparticle and reflecting it in a mirror. Until that moment, CP symmetry had been assumed to be as inviolable as CPT. Cronin and Fitch's result, which won them the 1980 Nobel Prize, proved that nature does, in fact, distinguish matter from antimatter under certain conditions. In 1967, Soviet physicist Andrei Sakharov laid out 3 conditions any theory would need to satisfy to explain why the universe contains far more matter than antimatter: baryon number violation, departure from thermal equilibrium in the early universe, and critically CP violation, exactly the kind of asymmetry Cronin and Fitch had found. It seemed, for a moment, like physics had the missing ingredient. Then the numbers were run. The amount of CP violation observed in kaon decays, and later confirmed in B mesons by the Babar and Bell experiments, and in 2017 in baryon decays by the LHCb collaboration at CERN, is real, measurable, and repeatedly confirmed. It is also far too small. Calculations show the known CP violation in the Standard Model falls short of explaining the observed matter-antimatter imbalance by roughly 10 orders of magnitude. The Planck satellite's measurements of the cosmic microwave background pin that imbalance at just over 6 protons for every billion proton-antiproton pairs that should have annihilated completely in the universe's first instance. Physicists have spent 60 years hunting for additional sources of CP violation in neutrino oscillations, in hypothetical new particles, in physics beyond the Standard Model, and have not yet found enough. We know the rule was broken. We have never found the full reason it was broken enough. Number 1. You are the rounding error that survived. Run the universe's clock back to its first fraction of a second, when temperatures exceeded 1 trillion degrees and every collision carried enough energy to conjure particle-antiparticle pairs directly out of radiation. Standard cosmology and particle physics agree completely on what should have happened next: matter and antimatter, created in equal quantities, should have found each other, annihilated completely, and left behind a universe of pure light photons, and nothing else. No stars, no galaxies, no planets, no observers to ask why. That is the rule, derived independently from quantum field theory and from measurements of particle collisions in every accelerator ever built. Matter and antimatter annihilate in pairs, leaving nothing behind but energy. Unless something breaks the balance first. Something broke the balance. For every billion or so antimatter particles in the infant universe, there were 1 billion, and 1 matter particles, a measured imbalance of roughly 6 parts in 10 billion, confirmed by Planck satellite observations of the cosmic microwave background and by measurements of primordial element abundances. When annihilation finished its work an instant later, that tiny surplus was all that remained. Every proton in your body, every atom in every star ever photographed is built from that leftover fraction of a percent. The rest, the overwhelming majority of all the matter that ever existed, became the photons that now fill the cosmic microwave background. The faint afterglow still detectable in every direction you look. Physicists across CERN, Fermilab, and dozens of neutrino and collider experiments worldwide are actively hunting for the missing physics that could explain an asymmetry this large. New sources of CP violation, exotic decay processes for neutrinos, physics not yet described by any existing theory. None has been confirmed. The Standard Model, tested and retested to extraordinary precision everywhere else, cannot account for your own existence. You are not made of the universe's substance. You are made of its accounting error. Every atom in you is a fragment that annihilation forgot to erase, a rounding difference from a calculation performed before the first star existed, and to this day. No one can fully explain why the universe rounded up instead of down. If you want to see more videos like this, click the video on screen now, and make sure to subscribe.